very similar to alkenes, alkynes undergo addition reactions because they contain weak, relatively weak, pi bonds. And so two sequential reactions can take place. You can add one equivalent of a reagent to form an alkene, and then you can add a second equivalent of a reagent, and then you can form 4 sigma bonds. Now, we are going to look at 4 different types of reactions in this screencast, and many of these have the same mechanism as alkenes do, but some of them there are differences, and so we're going to talk about some of those differences that we encounter. Alkenes, as a reminder, are nucleophiles. I said alkenes. Alkynes, right, are nucleophiles like alkenes, right? And they will react with electrophiles. Okay, so we're going to discuss these 4 addition reactions, but we need to talk about terminal alkynes first, because terminal alkynes have some kind of unique chemical properties we need to go over. So when we talk about a terminal alkyne, shown here, right, these carbons are sp hybridized, and the sp hybridized carbon-hydrogen bond is considerably more acidic than sp2 hybridized carbon-hydrogen bonds like in alkenes, or sp3 hybridized carbon-hydrogen bonds. So that means that terminal alkenes are pretty readily deprotonated with a strong base in a Bronsted-Lowry acid-base reaction. Now this results in an ion called an acetylide ion, which we see here, which then, it's really cool, can go on and react with an electrophile and form a new carbon electrophile bond. So this is very versatile in organic synthesis. Now, when we choose bases to do this reaction, when we think about what bases we can use, we need to use bases with conjugate acids with pKa's higher than terminal alkynes. Now, terminal alkynes, it's up there, but I like to have it here too, have a pKa of 25. So that pKa needs to be greater than 25. Those are strong enough. And so, for example, the bases here, NH2 and a hydride, are strong enough. A hydroxide and a deprotonated alcohol are not strong enough. So amines are really the way to go, right? Or hydrides. Those are what we're going to see that can deprotonate that, that terminal alkyne bond. Now, we're going to talk more about this in the next screencast and how that acetylide ion can then react. So without further ado, though, let's jump into some of our addition reactions. So the first one we're going to talk about is hydrohalogenation. Alkynes undergo hydrohalogenation when you add hydrogen halides, so HCl, HBr, HI. 2 equivalents of the hydrogen halide are generally used. The addition of 1 mole of the hydrogen halide forms a vinyl halide, shown here, and then that reacts with a 2nd mole of the hydrogen halide to form a geminal halide, shown here, where we have 2 of the 2 halogens here connected to the same carbon. Now, this is an example of an electrophilic addition. Because the electrophile which here is the proton. Is attracted to the electron-rich triple bond. Okay, so these are classified as electrophilic addition reactions. Now, I want to remind you, hydrohalogenation follows Markovnikov's rule. So when you look at this, neither carbon has a hydrogen that's attached, right? And so when we add that first hydrogen that's attached, now the second hydrogen will attach to it as well, and there's where you get the geminal dihalide. With a terminal alkyne, you've already got a hydrogen here, so during the first addition, the second hydrogen will go there, and then during the third addition, we'll see the third go there. So both of these end up with the halogen on the same carbon. Now, if you only use one equivalent, the reaction does stop with the formation of the vinyl halide, which is shown here. So let's look at that mechanism. All right, so we are looking at a terminal alkyne, and let's add HBr. So the first step is that this is the nucleophile, and it's going to be attracted to an electrophile. When we look at this bromine, the bromine is partially negative, the hydrogen's partially positive. So if this is a nucleophile and this is an electrophile, they're going to be attracted to each other. So these electrons come out and attack that proton and pull it back. Then these electrons go on to the bromine. And now what we have is a double bond with two hydrogens that are attached, okay? Then we also have a positive charge right there on that carbon. So the bromine acts as a nucleophile and comes and attacks that carbon. And so now that's the product that we have. Now, I drew the two hydrogens in so you could see the hydrogen joining there. Notice I've left the hydrogens off. Remember, with these stick structures, it's just understood there's hydrogens there. So that is what makes this tricky sometimes when we come back in and we have to think of Markovnikov's rule and say, okay, hey, look, I know this is going to come and play again, right? It's going to grab that proton. Those electrons are going to go on that bromine. And so you have to remember right? That I don't like that molecule at all. Let me erase it and try again. I'm going to move that bond down and that bromine over, and then I'm going to have it like that. There we go. All right? So you have to understand that it gets pulled back and it goes there, okay? Now, the bromine comes in, right, and attacks that positive carbon. And now we get two bromines attached to the same carbon. Now, I want to remind you, you are forming carbocations. So, watch out for rearrangements. Anytime you form a carbocation, we have to watch out with rearrangements. A few other things here, just to note about this. The electrophilic addition of HX to alkynes is slower than the electrophilic addition of HX to alkenes, right? Even though those alkynes are more polarizable and have loosely held pi electrons. The other thing to note is that this intermediate here is resonance stabilized. So when we talk about this being resonance stabilized, we have two resonance contributors here to give us the resonance hybrid here. And so the halogen here stabilizes this adjacent positive charge by resonance, which is one of the reasons we see this following Markovnikov's rule, right? So that positive charge gets delocalized. Let's look at halogenation. Okay. Halogens, which are again the halogenation, which uses the X2, right? Dichloride, dibromide, Br2, Cl2, add to alkynes just like they do with alkenes. Addition of 1 mole will give you a trans dihalide, and then a second one will give you a tetrahalide. And so this is the generic, this is the example with a specific example. And that's it. They follow the same mechanism. As alkenes, it just does it twice. That's it. Okay. Let's talk about hydration. When we talk about hydration, in the presence of a strong acid or a mercury catalyst, what happens is the elements of water add to the triple bond, and they form something called an enol. Now, an enol is when you have a double bond next to an OH. Right, so double bond OH, we have an enol here. Now, this enol is unstable and can rearrange to a ketone, which we see here. And we're going to look at that mechanism in just a second. Now, when it rearranges to the ketone, there's a carbonyl group. And what we see is that internal alkynes, right, when they go through this reaction, they are fine using a concentrated acid. There's an enol, there's a ketone, and they rearrange. When you have terminal alkynes, they generally are the ones that require the presence of a mercury catalyst, usually mercury sulfate, and that gives a methyl ketone. And then, I was here at the enol, but it gives a methyl ketone here. And that's a Markovnikov addition of water, where the hydrogen is going to add to the terminal carbon. There's already a hydrogen there. And so we rearrange into that methyl ketone. So I want us to look at that keto-enol rearrangement. That's a new kind of phrase that we're talking and throwing around. So let's look at this for a little bit. So here we're going to introduce the term tautomers, right? And these are constitutional isomers that differ in the location of a double bond and a hydrogen atom. Right? So A and B are tautomers. So A is the enol form here and B is the keto form here. The enol tautomer has the OH group bonded to the carbon-carbon double bond here. The keto tautomer has a carbonyl instead. Okay. Now, equilibrium, so if you look at these two equilibrium arrows, equilibrium favors the keto form because the carbonyl is much stronger than the carbon-carbon double bond. sorry, my because got really wild there, because the carbonyl is much stronger than the carbon-carbon double bond. Now, tautomerization is just the process of converting one tautomer into another, right? And this can be catalyzed by both an acid and a base. So let's look at the mechanism. Here, we have our friendly enol. And this is, we're looking at an acid. And so one of the things that signals to us that we're in an acid is that we have H3O plus there. And so this double bond comes out and it's going to grab that proton. And those electrons are going to go back on the oxygen, and that's going to form water. When it pulls the proton back, the proton is going to add to the carbon with the more hydrogens, which is going to be that carbon there. And so you end up then with this, okay? Now, these electrons come down here to form a double bond. When that occurs, you then get a positive charge on the oxygen, and water will then come and remove that proton, and those electrons will go back on the oxygen. Excuse me. And then we now have our keto version. So let's put this all together with a hydration mechanism. All right. We are going to take this triple bond and we are going to add an acid. Okay. And because we've got acid and water, and it's going to come out and it's going to steal that proton, and those electrons are going to go there. Now, when this occurs, the hydrogen can add to this side or this side. This is an equivalent molecule either way. So we come here, right, and we say, okay, now we've got a double bond here, just like that. And I am going to put my positive charge here. Now, the hydrogen added here, right? But we're not going to show it because it's a stick structure. And so what happens then is that water comes along, right, and acts as a nucleophile and is attracted to that carbocation. Now, when this happens, right, we get a protonated alcohol, and water removes that proton, regenerating the catalyst. So our catalyst is regenerated there. And so now we have that double bond, right? Now, this is a enol. So you got to watch for it because it's not going to tell you anything. You just got to know that's an enol. So you got to be able to recognize it. Water's going to come in again, or sorry, I said water, but it's the acid, the protonated water. And the double bond's going to act as a nucleophile and grab that proton. Those electrons are going to go back on the oxygen. Right? When this happens, we have no hydrogens here. We have one hydrogen here. That proton is going to come back and join on this side. We're not going to show it because we're drawing a stick structure. If that makes you uncomfortable, if you're like, ooh, I do not like that, Dr. Pierce, you don't have to draw a stick structure. Draw the whole thing out. It's really whatever helps you. Stick structures tend to be faster, but if you are messing up and can't keep track of your hydrogens, draw it all out. That is my suggestion there. All right, so we've got this guy, right? And what we're going to see here is that we've got resonance. And so these electrons are going to jump down here, okay? And when that happens, you end up with a positive charge on your oxygen. And this is where water comes in and it grabs that proton, and those electrons go there. And so now we have our happy ketone. So we've just really put the two mechanisms together, right? We've undergone a hydration reaction, which we have seen before. And then once we form an enol, right, we go through that keto-enol tautomerization to form the ketone. Now, our last reaction that we're going to look at in this screencast, our last addition, is the hydroboration oxidation of alkynes. This is a two-step reaction sequence that converts the alkyne, right, into a carbonyl compound. So addition of the borane forms an organoborane here, and then we undergo oxidation after that to form an alcohol. And when we form that alcohol, look, it's an enol, and then it'll go through the tautomerization here. So this follows the same mechanism from the previous chapter, and then this is the enol keto tautomerization that we talked about. Now, when we compare an internal alkyne to a terminal alkyne, hydroboration oxidation of an internal alkyne forms the ketone, right? Just like the acid catalyzed hydration did. However, when you undergo the hydroboration oxidation of a terminal alkyne, that's going to form an aldehyde here. The reason for this is that BH2 adds to the less substituted terminal carbon, right? And that results in an anti-Markovnikov's addition of water. So the BH2 adds to the less substituted terminal carbon, right? Resulting in anti-Markovnikov's addition of water. Right? And so those are the two products that we can form there. All right, we have finished up the addition of alkynes, much of which is very similar to the addition of alkenes. In the next screencast, we're going to look at reactions of those acetylide ions. As always, if you have any questions, please feel free to send me an email or ask in class or stop by my office. I'm happy to help.